Pseudorandom Correlation Generators from LPN.
Great, thank you, Let. First, I'm going to take a segue and plug a LaTeX editor that my friends are making that have helped a little bit. So if you're tired of overleaf, check out Cricket. Yeah, it's good. Yeah, that's just an ad. Great. So at this point, I think we're all familiar with MPs. Exactly. You got to take advantage of a captive audience. Yeah, MPC. So I'll be mostly focusing on the gate-by-gate model, where you have some function, and you want to evaluate it gate by gate. So the first half of the talk, I'll be talking about binary circuits mostly, and there you want these binary triples essentially. And then and the main algorithm that people use, at least in the two-party case, is this Beaver triple trick, where if you pre-process a random triple x, y, z, such that z is the product of x and y, you can then use this sort of clever de-randomization technique to compute the result of A times B, where A and B are chosen, but secret shared, and you get the secret shared result. So I'm sure everyone knows Beaver. At least a lot of people do. Yeah, so then this sort of is a chicken and egg problem. You can multiply if you can multiply. But the nice thing is that these x, y, z Beaver triple can be random. And so then the question is, how do you generate these random Beaver triples? And for the first half, I'll be talking about doing this from oblivious transfer, and how do you generate a lot of oblivious transfers. And the second half of the talk, I'll be discussing arithmetic Beaver triples over some like FP, for example. Yeah, so how do we build these oblivious transfers? It'll actually be easier if we just directly talk about vector oblivious linear evaluation, VOL. I guess Peihan was talking about this a little bit yesterday, and the protocol, there's some setup protocol called VOL, and it outputs essentially a secret sharing of a scalar delta times a random vector A. So one party holds the scalar, one party holds the vector A, and then you also get a secret sharing of it. Sometimes it's written slightly differently. There's like a minus somewhere, but whatever. Let's do this one. And then once you have this VOL correlation, these vector might be length 1,000,000 or something, to give you context. You can convert these into a million oblivious transfers by applying a hash function appropriately. And then once you have oblivious transfers, you can just look at the least significant bits, and you have a binary Beaver triple, essentially. And so this is currently one of the fastest ways of getting these binary Beaver triples. And then the question is, OK, we have how do you build VOL? Let's keep going. Oh, as a little segue, VOL isn't just useful for generating binary triples. You can use it to do all sorts of things, zero-knowledge proofs. We saw PSI yesterday. Yeah, OTs, and some ideas also like going over into post-quantum cryptography, which is sort of interesting. OK. So how do we do VOL? There's a setup protocol, and what we want is that the setup protocol should output some succinct keys. And I'm sorry, I keep getting kicked out. Zoom is causing problems. OK, I think. Yeah, so we want a setup protocol which will output these two small keys. And then we want to be able to locally expand, only do local computation, no more interaction between the parties. And the setup should be small. So if your vectors are length n, we would want the communication to be like log n or something like that, and non-interactive. And then at the end, we want our correlation, our vol. Vol. So one party holds delta, one party holds A, and you have a secret sharing of them.
So this is just one way to achieve this functionality. There are other ways, right?
Right.
How does it compare to other ways? Like,
This is the way you should do. This is the best.
is this clear that this is the best way to do?
Until the next great idea, yeah. I think, yes, this is certainly the, if you want vol or OT, I mean, there are some,
This is symptomatically there are better ways. If you count just the time of the computation, not the communication. So, I mean,
yeah.
so I'm not sure that the answer is that I buy the answer. Depending on the context, probably.
Well, my subjective opinion is this is the way you want to do it. It has a lot of nice properties. Like communication ends up being like the main cost. This gives you sublinear. The computation to actually do this expansion is extremely CPU friendly, as we'll see. So it ends up being very nice. If we can come up with a better way, amazing.
there are alternative ways. So I don't know. Like,
But I guess
it would be nice to see a comparison, like in terms of communication and computation between this approach and other ones.
You'll be disappointed. This is all we're doing. But yeah, I agree. There are other ways. Yeah.
So here A is a 0, 1, where 0 is the additive identity and 1 is the multiplicative identity. Is that how you're doing?
Yeah, there's different, I'm sort of glossing over this fact. There's different variants. Sometimes delta is over a field and A is binary.
That was my next question. Is it characteristic to field or like?
Yeah, typically. But there's also other variants when you do vol. A will also be like field elements.
I see. So A is
different flavors.
the base field. Okay.
Yeah. Yeah, and delta could be over an extension field. All combinations have applications, essentially.
I have a question.
Yes.
By k log n communication, do you mean the bit size of k0 or k1?
I guess k, I just mean like security parameter, and maybe it's even like k squared or something. But
Right. No. My question is, what do you mean by k log n communication? Do you mean the bit size of k0 is k log n?
yeah, that's one way to think about it. Or the protocol to run it, to set it up. Yeah, they're sort of the same thing. Yeah. Okay, good. So this is the correlation we want, and we want this property. And this is sort of this so-called silent property where there's only a small amount of communication. And yeah, and in MPC, communication ends up being the main issue, and so this is sort of why people like this paradigm. And this is called a PCG, I guess, I mean, more generally. Okay, so how could we realize this? There's a cool protocol called a punctured PRF protocol, based upon the GGM tree idea, and it. We're not yet going to zoom into that box, but the output of it is almost what we want. It's sort of the same correlation exists, except for it's sort of like low quality, in that this A vector is extremely sparse, almost 99% zeros. And then the question is there a way to bootstrap this sort of sparse version, which for some reason is efficient to generate, which we'll talk about? Is there a way to bootstrap this sparse version into the desired version where this A vector looks uniformly random? The answer is yes, but first, I guess let's talk about how we generate this vector. So I just turn these vectors horizontal. And then to simplify the explanation, let's not say A is sparse, but let's say A is actually a unit vector. And then how do we generate this even sparser version of the correlation? Well, as many of you can guess, you use a tree, punctured PRFs, and distributed point functions, the basic algorithm. And the idea is the sender will pick some seed of a binary tree and then use a PRG to expand it to get a bunch of leaf values. And these are all be sort of random values. And there's a special root to leaf path that the receiver, who knows the index, the receiver knows this vector, so they know the position that it's at. But what they want is a secret sharing of delta at this position. And there's this sort of clever algorithm where you can, for the seeds that the receiver is allowed to learn, you can use an oblivious transfer for each level and pick up the seed that that the other receiver is allowed to learn, and expand the corresponding subtree, pick up the next seed they're allowed to learn on the so-called co-path, and keep expanding the tree until you get to here, and then you do something slightly different where you let them learn the co-path seed, but also at the special position, they don't learn the seed, they learn the seed plus delta. And somewhat amazingly, when you first think about this functionality, you'd think you'd need communication proportional to the number of leaves, but there's a clever trick using only summations that let you to do this sort of totally obliviously. This is you can also, if you're more familiar with a distributed point function, that would also get you this.
Why would it be proportional to number of leaves? It seems like you're just doing kind of communicating about the path. Like
Right.
It's
So,
directly learning the seed on the co-path.
right. So that, yeah, it is just log communication, but I'm saying like, if someone didn't tell you the protocol, you might think you can't do
Oh,
it.
okay. Yeah.
I'm just
Now
saying
you're
it's
telling
clever.
me.
Little bit.
So it only requires log communication. Yeah. OK, so once we know how to do something once, you can essentially do it multiple times and get, so we can get a secret sharing of a unit vector where the value at the unit is delta. And then we can repeat this the number of times that we want. And since the number of non-zeros is like small, maybe security parameter, this ends up being OK.
So Peter, is there a better way to do like a k-sparse vector rather than repeating k times the unit solution?
Is there a better way to generate this? Is that the?
I mean, you showed us this nice solution for us, when you have a single entry and now you want to move to k entries, k non-zero entries, and the naive thing is to do it k times. I'm asking whether you can speed it up.
Yes. That's like the last slide, maybe. But yeah, there are some cases where you can do other tricks and sort of avoid the problem completely. Well, instead of doing repeat, you can do concatenate, which maybe works in some cases, but in other cases, there are better ways, which you get, yes.
But there is no direct solution kind of that generalizes the single entry in the tree kind of structure.
There is. Alet and others have a paper that generalizes algorithm to but there's a lot of different dimensions, different ideas of how to go instead of doing repeat. Yes, and there's more work to be done. So if someone's motivated, there's, yeah. Okay, so we now have an idea how to generate secret sharing of a sparse vector times a scalar. And the magical trick, the last magical trick, is how to go from the sparse version to the sort of fully random version. And there we apply this problem called LPN, or syndrome decoding, depending on your preference. And the basic idea is that the parties will agree on a random-looking matrix G, and they'll just do matrix vector multiply. And the magic of LPN is that this sparse vector will now look uniformly random, but shorter, maybe half the size. And that's how we generate vol. And then so each one of these can be used, each position in this vector could be used for an AND gate in your larger MPC protocol.
So Peter, you mentioned that there was security parameter, the sparse vector, but is it really security parameter? How sparse it needs to be? Doesn't that should be like some rate 1/dimension or something?
I think it's security parameter. It can even be like under security parameter. Like half the security parameter. You can choose parameters.
What you need for the LPN security. It's really just an error vector in an LPN.
Yeah, but the error vector in LPN is as long, it's a rate proportional to how many sample you have, right?
Yes.
And I suspect the G matrix is gonna be at best a square. Let's say it's a square, then it's like the best rate. But then
No.
the sparse matrix is gonna be the number of the length of the density, like divided by some.
You can. It's shocking actually, especially I don't know if
Into
we'll
the
talk about
delta,
like
yeah.
the weights don't need to be so bad.
Yeah.
But there's probably less offline.
Yeah.
I just don't know if it's a fixed security parameter, but I think it's like arbitrary polynomial ratio that is.
So when you're in the LPN world, you kind of want a good stretch. But when you switch to the dual LPN world, you don't really care about the stretch as much. Like stretch 2 is like perfectly fine.
Yeah, exactly this picture, yeah.
Yeah.
That's a reduction.
Right. Right, normally you want this R vector to be much longer than S. Or like,
Yeah.
But in our
Yeah.
case, like a factor 2 is amazing.
Yeah, then your noise vector is actually m divided by the rate, right? The sparsity is m times rate.
You can take it offline maybe. I'm not the most sure about it, but I know what parameters come out of like this. Yeah.
Like the easiest, like simplest conclusion is that, right? I mean, you could kind of exhaustive search over the noise in times and over the
Right.
choose the sparsity. So up to log n factors, the security parameter should be like roughly the same as the number of noisy elements.
Right. That's essentially.
That's without doing anything smart, right?
Right. Brute force search is essentially our best algorithm on this problem for this parameter regime. And that's how you can set parameters. Slightly better than that, but whatever. Okay, yeah, so maybe people are familiar with LPN. It looks like on the left, but we're using this other version called dual LPN or syndrome decoding, where you can get rid of the S vector, and so we're just compressing. It's sort of a cool homework problem to find the equivalence between these two and go back and forth, but they are the same problem. Okay, we can move on. Yeah, so we want to generate millions of, like this vector, we want it to be like a million or maybe even longer. And if you're worried about performance, this might seem like a problem because we want to do matrix vector multiplication, and this vector is length 1,000,000. It means G has like 1 trillion coefficients in it, and so that's naively doing matrix vector multiplication is going to be extremely slow. So how do we get around this problem? And classic LPN says pick G uniformly, but like many people in this space is you don't choose this matrix G uniformly random, but you want it to be some matrix such that matrix vector multiplication is extremely fast. But you also need this LPN problem to remain hard. So how do you choose this G matrix? Yeah, as I said, we want fast matrix multiply. But sort of the critical property, more or less, that we need, it's at least necessary, is that this G matrix to have high minimum distance. And this sort of impacts the best attack algorithms. So as long as your G matrix has quote-unquote high minimum distance, which means like a good error correcting code, a generated matrix for a good error correcting code, and you multiply like this, with a few exceptions, we believe security to hold. So then the question is, okay, this is our like criteria. What should we choose for G concretely? There's like the post-quantum coding community, and they use like this quasi-cyclic codes, and this is what we originally used as well. And this corresponds to polynomial multiplication, where you have like two polynomials, and you like do polynomial multiplications on each half and add them together. Mod something. But then the main bottleneck in this approach is the FFT, which is n log n time, to do the polynomial multiplication. So this was our starting point. It served us decently well at the beginning. But then I really like optimizing things, maybe too much. And we came up with this new code, which isn't no longer polynomials, but just sort of normal combinatoric code. It was extremely fast. Unfortunately, we didn't have a proof of security, no proof of minimum distance, but we had some evidence. Unfortunately, we were wrong, and it was totally insecure. Do not use silver. But
on purpose to teach the community a lesson.
right. I don't know if I've learned the lesson, but maybe others have. Yeah, but that's okay. It leaves room for follow-up works. So we didn't have a proof of what the minimum distance of this code was. So we ran some experiments, and it looked like the line was going up and right. It goes up and right, and then it goes flat right after where we couldn't compute it. And so, yeah, be careful with just assuming lines keep going up. Concretely, we found a linear combination of the rows or whatever that is 0 with not being very many. Yeah, we should have read the literature a little more, but I think this coding theory, the coding community has a very different language oftentimes, so it's sort of hard to parse, at least at the time. I let Peter, Yuval, and others, sort of around the same time, came up with this idea of expand accumulate codes. These codes are sort of nice, have some very cool properties. They're not nearly as fast as the silver, but we're probably faster than quasi-cyclic. But crucially had a proof that they're actually good codes. To improve this, we actually took ideas from silver and this expand accumulate, and we came up with this expand convolute paper, which did have proofs, which is great, and where it was even faster. And then very recently, still haven't put on an ePrint, but we have some very, I think, cool results, which we call block accumulate codes, which look like this maybe, which are going to be even faster. So how fast is all this stuff? Because here we're caring about like running time and everything. So originally maybe it was like 2 seconds or 0.2 seconds for a million. Silver was extremely fast, 11 milliseconds for a million OTs, which is ridiculous. But not secure. Expand accumulate is a faster improvement. Expand convolute was quite a bit faster, which is great. Our newest code is maybe down around 20 milliseconds, so we're getting back to around silver speeds. But what's sort of fun is we finally made it onto the GPU, and we got it down to just 3 milliseconds on a GPU. So extremely fast. That corresponds to 1/3 of a billion OTs per second on my laptop. So
These numbers are just for the multiplication or for the full expansion also?
no full expansion. But I think you can throw the expansion. With other tricks, you can put the expansion on the GPU. It'll be very efficient. So I think this is the number that the expansion should be less than this.
And is it clear that you don't have the tax about on these things? Like the distance is good that you prove, but other than that, I mean, is there any evidence?
Is there any evidence that curves are secure? I mean, I don't know.
Well, for random code, you have an evidence because you have a reduction to search problem. Here, this is a distinguishing problem which is much more fragile, and
right.
Other than that, I guess that much more people looked and tried to crypto analyze the curves. I'm not sure how many people looked at this code, right?
Right. That's
to be fair.
I agree. The answer is we have this quote unquote linear test framework which says high rate, but so there are the best attack algorithms don't seem to work, and there doesn't seem to be any good ideas that could take advantage.
I think the fundamental difference between curves and this is that here you're only expecting good amortized performance, whereas for curves they're really shooting for tight security. So really here you have huge margins because you can say that your best. You can design the system to resist attacks of time 2 to the 10,000.
So this is the way these things are set, like the amount of noise
just that you can afford. You don't need, again, maybe I'm wrong, but I'm saying in this context of amortized complexity, you have much more freedom to take margins.
Do you choose the margins?
Time aside, maybe this should be taken offline, like a couple minutes left.
Yeah, I'm definitely not doing the second half of the talk, so that's okay. Yeah, last time I gave this talk, I was under time because now I'm not even close. Anyways, we have more ideas to make things even faster and get back to silver speeds even on CPU. Okay, second half, let's speed run it. So for binary circuits, OTs and so-called degree 1 correlations are fine because you can like create binary triples from OT. But if you want to work over like FP circuits, arithmetic circuits, we need is a way to write like half of a Beaver triple where instead of being vector scalar multiplication, you want vector-vector component-wise multiplication. So sharing, and so you want this type of correlation called OLE or half of a Beaver triple. And maybe, if you want this D thing not to be a scalar, could we just like apply the same trick? Maybe, does it even make sense? Like, not really, this picture, but we want this picture to make sense. So there's some clever tricks I was hoping to get to, but I should fast forward. Instead of viewing things as sparse vectors, we switch over to being sparse polynomials. There's some sort of component behavior happening when you evaluate polynomials. There's like component-wise multiplication in the evaluation domain. We take advantage of that. We had to randomize things some more. Yeah, so by switching to polynomials, we have like this component-wise behavior. That's sort of like the crux of this next improvement. And then there's this other observation that you want a secret sharing of the product polynomial of these two sparse evaluations. And again, you can do this using the same basic formula, is that but now we have to take like the tensor, all pairwise combinations to get a sparse product polynomial. And these, when you evaluate it, will give you product, component-wise product multiplications. Yeah, so I guess, yeah, running low on time, so I won't get into too much detail. But basically, polynomials are cool. They let you get this component-wise multiplication. And then there's more recently, so what have I been doing lately? So this ring LPN paper was from like 2019 or well, I guess that's wrong, 2019 or 2022, depending on what. 2020 or ePrint 2022, maybe. Yeah. Anyways, it was in crypto 2020. But then more recently, no one's really been implementing. There was another implementation paper recently, but the vanilla version of this protocol is quite expensive because you need like security parameter squared point functions to generate this thing, which ends up being the bottleneck. And so there's been some recent improvements. So there's this idea of stationary. If you're worried about the previous assumption, close your eyes. There's this idea of stationary that I recently have at crypto is that like you can have many instances of this thing where the positions of the noise are fixed, but you just change the value for each instance. And so like you can just change the color of the slides and it stays secure. We tried our best to break it. Maybe there's more attacks, but it seems to fundamentally resist all attacks that we know. And this allows you to amortize the cost of this thing, and then it becomes even faster. We also recently have some improvements to set it exactly your question. Can you do something better than a naive summation? And the answer is yes. You can somehow reduce this to many small point functions such that the overall size is the same. Great. There's been a bunch of other really cool things. Other FFTs that are faster, going over this like trace thing, which recently came out in Eurocrypt. Very cool algebra going on there, in my opinion. So there's a lot of different ideas going on. Yeah, so on this slide, no cameras allowed. Because unlike some other people, I just made up these numbers. I wanted to give you a sense of how the performance improvement, these numbers are very rough, so I just sort of guessed, almost educated guess. So how's the performance for binary triples? For 1 million, using OT-based mascot, maybe it's like 160 seconds for 1 million FP triples. There was a FHE improvement. Low drive maybe gets down to 33 seconds. The Ring LPN paper I have implemented maybe 10 seconds. And then the new, with all these optimizations on the last couple slides, maybe less than a second for a million. The exact number is still sort of ambiguous.
This is, again, this refers to, say, 128-bit field.
I was more targeting like maybe 32 or 64-bit, but I mean,
Yeah.
there's margins to, yeah. Maybe we can take Srini's improvements.
Is there a simple way like to not talk about milliseconds, maybe talk about arithmetic operations, so you will get the same numbers, or?
Yeah. I mean, yeah, you could have a different metric.
But it will look the same, right? I mean.
Yeah, like this number to here is like number of AES calls reducing.
Okay.
And you could count them. There's asymptotic difference as well.
In terms of communication cost, of course, the things on the right are radically different than the two columns on the left.
Yeah, like this is like basically networking.
Okay, so
this
that
one
was
is
my question. Okay, so it will be, okay. I mean,
Yeah.
for me it will be more meaningful to understand like, is this like communication gaps or number of operations, or what are you measuring, and because this is probably on different platforms.
right, they are. And also slightly made up, but I tried. I was literally like implementing stuff yesterday, so it's quickly moving.
And in the case that this is the end, then.
Yeah.
Okay. So yes, and so let's start the break, but feel free to ask Peter more questions.